Okay, in the previous class we already discussed about the directional derivative and the maximum directional derivative of the function and the minimum directional derivative of a function. Okay, then we look for a question. Let f of xy equal to x square a raised to y. Find the maximum value of the directional derivative at -2, 0 and find the unit vector in the direction in which the maximum value occur. Okay, what this question says that we given a function f of xy equal to x square a raised to y. We want to find the maximum value of the directional derivative, that's equal to norm del f, that is the magnitude of the gradient vector at the point -2, 0. Also we want to find the unit vector in the direction in which the maximum value occur, that's equal to del f by norm del f. Okay, here given f of xy equal to x square e raised to y. We have that the maximum value of the directional derivative is norm del f. Okay, where del f is the gradient function, that's equal to del f equal to fx I cap plus f by j cap, where fx is the partial derivation of f with respect to x, where fy is the partial derivation of f with respect to y. Then fx is equal to 2x e raised to y and fy equal to x square e raised to y. Then we get del f equal to 2x e raised to y I cap plus x square e raised to y j cap. Then the value of del f at the point -2, 0 equal to substituting -2 for x and 0 for y, then that is equal to 2 into -2 into e raised to 0 I cap plus -2 square into e raised to 0 j cap, that's equal to -4 I cap plus 4 j cap. Then we want to find the norm del f, which is the maximum value of the directional derivative, that is norm del f equal to square root of 16 plus 16, that's equal to 16 plus 16, that's equal to 4 into root 2. The unit vector in the maximum value occurs, okay, in the direction of, that is the maximum value of the directional derivative occurs in the direction of del f by norm del f, which is the unit vector. We calculated del f and norm del f. Then the unit vector del f by norm del f equal to -4i plus 4j by 4 root 2, cancelling 4 commonly, then we get to -i plus j by root 2. Okay, then we have a next question. Find the directional derivative of f of x y z equal to x square y minus y z cube plus z at the point 1 -2 0 in the direction of 2i plus j plus 2k. That is, we want to find the directional derivative of f of x y z at the point 1 -2 0 in the direction of 2i plus j plus 2k. Okay, start. We want to find the directional derivative of f of x y z, that's equal to du of f equal to del f dot u cap, where del f is the gradient of the function, that is del f equal to fx I cap plus fy j cap plus fz k cap, and dot product with respect to a unit vector u cap. But here given the vector is which is not a unit vector, then we convert this vector into unit vector by dividing the vector with respect to his magnitude. Okay, here f of xyz equal to x square y minus yz cube plus z. Then we want to find fx, fy, fz, then we substitute that values in del f, then we get the value of del f, that is gradient of that function. That is fx is equal to xy, fy equal to x square minus z cube, and fz equal to minus 3y z cube plus 1. Then del f equal to 2xy I cap plus x square minus z cube j plus minus 3y z square minus 1 k cap. Then the value of del f at the point 1 -2 0 equal to substituting 1 for x, -2 for y, 0 for z. 2 into 1 into -2 I cap plus 1 square minus 0 j cap minus 3 into -2 into 0 minus 1 k cap, that's equal to -4i plus j plus k. Okay, then we want to find the unit vector. Here the given vector is not unit, then we want to find a unit vector corresponding to the vector 2i plus j plus 2k, that's equal to u cap equal to 2i plus j plus 2k divided by whose magnitude, that is root of 4 plus 1 plus 4, that's equal to 2i plus j plus 2k divided by root 9, that's equal to I plus j plus 2k by 3, that's equal to 2 by 3 I cap plus 1 by 3 j cap plus 2 by 3 k cap. That is, we find the gradient of that function and a unit vector u cap. Then the directional derivative of f at 1 minus 2 0 in the direction of u cap is du of f at the point 1 minus 2 0 equal to del f dot u cap, that's equal to minus 4 I cap plus j cap plus k cap dot 2 by 3 I cap plus 1 by 3 j cap plus 2 by 3 k cap. Taking dot product with these vectors, then we get minus 8 by 3, that is the coefficient of I into coefficient of I. Okay, that is minus 8 by 3 plus 1 by 3 plus 2 by 3, that's equal to minus 5 by 3. Okay, then next question, given that the directional derivative of f of xyz at the point 3 minus 2 1 in the direction of 2i minus j minus 2k is minus 5 and that norm del f at the point 3 minus 2 1 equal to 5, find del f at the point 3 minus 2 1. Okay, we want to find the directional derivative of this function. Sorry, we given the directional derivative of the function f of x y z is minus 5 at the point 3 minus 2 1 in the direction of the vector 2i minus j minus 2k. Also, we given an additional condition, that is norm del f at the point 3 minus 2 1 equal to 5. We want to find del f at the point 3 minus 2 1. That is, we want to find the gradient of this function. Here only given the directional derivative of that function at the point 3 minus 2 1 equal to minus 5 in the direction of a vector, and also given norm of del f at that same point equal to 5. That is, rewriting the given condition, that is, given that du of f at the point 3 minus 2 1, that is directional derivative of f at the point 3 minus 2 1 in a unit vector equal to minus 5, and also given norm del f equal to 3 minus 2 1, that's equal to 5. Then we get du of f equal to minus norm del f, which is the not maximum, which is the minimum value, which is the minimum value of directional derivative, okay, which is in the direction of the unit vector minus del f by norm del f. That is, we already studied minus of norm del f is the minimum value of the directional derivative, which is in the direction of the unit vector minus del f by norm del f. Okay, given vector is 2i minus j minus 2k. Okay, we want to find the unit vector corresponding to this vector, that is dividing this vector with respect to whose magnitude. Okay, then we have u cap equal to minus del f by norm del f for the minimum value of the directional derivative. Okay, which gives 2i minus j minus 2k by root 4 plus 1 plus 4, which is the unit vector corresponding to this vector 2i minus j minus 2k, that's equal to minus del f by 5, when which implies that 2i minus j minus 2k by root 9, that's equal to minus del f by 5, which implies we cross multiplying 5 with respect to this, that's equal to minus 10i minus 5j minus 10k by 3 equal to minus del f. Then we get del f equal to minus 10 by 3 I cap plus 5 by 3 j cap plus 10 by 3 k cap. Okay, this is a different types of question. Okay, then we have a note, using an angle of inclination. If the direction of directional derivative is described by the given angle alpha of inclination of the unit vector u cap, then we can use the expression u cap equal to cos alpha I plus sin alpha j. That is, we given the angle of inclination equal to alpha, then the unit vector corresponding to that angle, that's equal to u cap equal to cos alpha I cap plus sin alpha j. Then next question is related to this, that is, find the directional derivative of f of xy equal to x square y cube minus y raised to 4 at the point 2 1. in the direction given by the angle theta equal to pi by 4. Also find the unit vectors which are in the direction of the maximum value of the directional derivative and in the direction of the minimum value of the directional derivative at 2 1. That is, we given a function f of xy, we want to find the directional derivative of that function at 2 1. Also given the angle theta equal to pi by 4 is the angle of inclination. Then we want to find the unit vectors in the direction of the maximum value of the directional derivative and also at the same time the direction in the minimum value of the directional derivative at the point 2 1. Okay, given f of xy equal to x square y cube minus y raised to 4. Okay, and theta equal to pi by 4, we want to find the directional derivative of f at 2 1. That's equal to du of f equal to del f dot u cap, where del f is the gradient of that function, that is fx I cap plus fy j cap plus fz k cap. Here only we have x y, z coordinate is 0, and also we want to find a unit vector. So we want to find a unit vector in the direction corresponding to the angle theta equal to pi by 4. That is, look for the above notes. That's equal to cos alpha I cap plus sin alpha j cap. That is u cap equal to, instead of alpha substitute here, pi by 4. That is u cap equal to cos pi by 4 I cap plus sin pi by 4 j cap. That's equal to 1 by root 2 I cap plus 1 by root 2 j cap. Then del f equal to fx I cap plus fy j cap, which is the gradient of that function. That is fx is equal to 2xy cube, which implies fx at the point 2 1 equal to 4 and fy equal to 3y square x square minus 4 y cube, whose value at the point 2 1 equal to 12 minus 4, that's equal to 8. Then we get the unit vector u cap and the gradient vector del f, then taking whose dot product, which gives the directional derivative of that function. That is, therefore at the point 2 1, the directional derivative gradient of f equal to 4i plus 8j, then the directional derivative of f equal to 4i plus 8j dot 1 by root 2 I cap plus 1 by root 2 j cap. That's equal to 4 into 1 by root 2 plus 8 into 1 by root 2. That's equal to dividing 4 by root 2 and dividing 8 by root 2, which gives 2 root 2 plus 4 root 2, which is equal to 6 root 2. That is the directional derivative of that function in the direction of that unit vector at the point 2 1 equal to 6 root 2. Okay, next we want to find the unit vectors which are in the direction of the maximum value of the directional derivative and the minimum value of the directional derivative. That is, we found that the del f, that is gradient of that function, equal to 4i plus 8j at the point 2 1. Then norm del f equal to root of 4 square plus 8 square, that is 16 plus 64, that's equal to root 80. We separate that into 16 into 5, that is root 16 into 5, that's equal to 4 root 5. Then the unit vector in the direction of the maximum directional derivative equal to del f by norm del f, that's equal to 4i plus 8j by 4 root 2, dividing 4 commonly, then I plus 2j by root 5, that's equal to I by root 5 plus 2j by root 5. Then the unit vector in the direction of the minimum directional derivative, which is in the opposite side of the maximum directional derivative, that's equal to minus del f by norm del f, that's equal to minus of I plus 2j by root 5, that's equal to minus I by root 5 minus 2j by root 5. Okay.